Welcome to the course Algorithmic Design, session number 6, recursion and grammars. And they are related topics. Often you would not find them together in a lecture, but through my research and my work, I realized that these topics are actually quite related. And I decided in this lecture to group them together. What is recursion? Here we start with the definition. This is from Wikipedia. So nothing really fancy, but it's good that you have these definitions here. And recursion basically, it's a computational concept where a thing or some entity or an object or a design is defined in terms of itself. And if we talk about mathematics, then, or in the context of mathematics, you can say there is a function. So function is some kind of a mathematical object which takes parameters and does a calculation and gives you a result. And the recursive function will be a function that has that contains itself. Okay, so it's a nested function that would contain itself. Contain itself in its own definition. And so you'll be like it's a recursive function. And turns out that many problems in the real world can be explained as through in a way subset of problems. Or so you resolve a big problem by explaining a subset of that problem, and that subset and the big problem are kind of the same problem. Okay, so you are breaking the problem down into smaller parts, but all the parts are actually the same. And that's kind of where recursion comes in, because it means that you can define an infinite process using a finite description. Okay, and directly related to that is the concept of a fractal. Okay, fractals are abstract objects. We often represent them as shapes, or images. Even though in some sense they're more abstract than that, and they're abstract objects which exhibit self-similarity in increasingly small scales. It is also known as expanding or evolving symmetry. So as you know, we can talk about symmetry of objects. That means we can sort of split an object into multiple parts, and then by performing we can either split the object in multiple parts, and then by performing very simple operations, we basically get this parts start looking the same, or parts look the same. Or when we transform an object, we can get it to a point where it looks exactly the same. So think about, for example, rotational symmetry. Or so if I have a square, I can rotate it for 90 degrees and it looks exactly the same. Okay, so that is the property of symmetry. So I can have rotational symmetry, translational symmetry. So if I have a square grid, and I do a translation of that grid, I basically get exactly the same shape. If I manage to align the grid, or so there's a certain phase in 2 dimensions, and if I perform translation, I get exactly the same shape or configuration. So that's translational symmetry. Fractals are example of expanding symmetry. Also, I can zoom in to an object and then it starts looking the same or similar, or it's not strictly the same, but the condition that it kind of looks similar. Okay, and this term was coined by Benoit Mandelbrot, who I think it was in the 60s, started exploring these structures through use of a computer, or because before that you could sort of define fractals, but it was very hard to visualize them. And computers were basically the first machines where we were able to see how they look like and see basically how complex they are. And then the word fractal comes from the Latin mean broken, because you will see these fractals look like broken shapes. Again, fractal shapes appear in nature. Okay, and that was one of the main motivations. Also, maybe Mandelbrot later, when he realized that many shapes in nature can be described as fractals. They are, of course, in some sense, imperfect fractals, but yeah, they have fractal properties, especially many shapes that are created by natural evolution, or so organisms and so on exhibit these fractal properties as well. So you see it in the inorganic world as well as the organic world, and we have a very clear definition in mathematics. So there are quite some. It's a very big topic. Okay, connected to fractals are so-called L systems or Lindenmayer systems. One of the texts at the very end that I recommended to you is from Lindenmayer. So I forgot the name exactly of the book. We'll check at the very end. I think it's called The Computational Beauty of Plants. It just describes plants through these L systems, or so it's and specifically in computational terms, this is a so-called parallel rewriting system. Okay, so at the very, I think it was the very first lecture of this course, I listed types of computational models, and rewriting systems were one of them. So yeah, and it's a type of formal grammar, or so it's yeah, it's basically mathematically defined grammar. Okay, so L systems, we can use them. There again, they use recursion to create shapes, and we will use them specifically today. I will show an example where we will generate a plant or tree in either 2D or 3D, and it's basically an L system. And again, today in computer graphics, these are used to create sort of organic looking trees and shapes, and I could also show you many examples of that, but maybe today there's not so much time to do that, but maybe later I can show you that they are very popular. So every time you see, in a way, a tree generated in a computer, it uses an L system, type of an L system to basically produce it. Nobody's modeling, you know, branches and leaves of a tree or canopy of a tree, you know, one by one in like Rhino. Nobody's doing that. This is done computationally. Okay, which also, again, interesting parallel is that we basically found, in a way, an algorithm that can describe all plants. Okay, so the way all plants are created, or at least how their shapes are created, which means the nature uses, in a way, similar rules to build up these same plants. And that was, I think, also, again, the main motivation of Lindenmayer to write his book. Basically, he was just kind of giving examples and trying to describe how all of the different, basically, flora of the world can be described through these computational rules. And of course, they have a lot of application, because today that means that we can generate plant-looking shape. We can generate plants in a computer, which of course has a, you know, you can think of yourself maybe as a, I think if you're a landscape architect, has application, but also if you're just working in the entertainment industry, making games, movies, and so on, this is the great way to create these models. And then the last topics, which is again very large, but here we are just tangentially going to touch on it, are shape grammars. Okay, so I said that L systems are a type of a parallel rewriting system, so type of a rewriting system. And shape grammars are also that, so they're part of rewriting systems, also called production systems. And it's basically grammar, formal grammar that we can use to generate shapes, or so. Yeah, so there we would have these so-called production rules, and we will start with basic primitives, and by defining these production rules of these primitives, which are basically shapes, we can create other shapes. And I'll show an example where this was used for generating, for example, floor plans, or describing the structure or configuration of Palladian villas. Okay, yeah, shape grammars can for sure be used in, and are directly applied in design, maybe even more in urban design rather than architectural, but in both of these are applicable. Okay, so those are just some basic definitions. And Now, just some examples. If you Google any of these terms, you will find a lot more examples, and I just try to show maybe a quick cross-section of them, so they're really easy to search for because they're just so popular. So, for example, Sierpinski carpet or Sierpinski triangle are types of fractals, so you can see them on top left and right, and you can see an example of this triangle basically being subdivided. Okay, so it's a fractal shape or fractal structure because we start with one triangle, then we divide it into, trying to count now, I guess 4, and then you get more triangles, and then you apply the same rule onto every triangle. Okay, so, and you basically do this if you want to have a, if you want to create a, or mathematically define a fractal, you do this ad infinitum, or so you do it infinitely many times. You get basically infinite complexity or infinite structure. Of course, in a computer, we cannot really do it infinitely many times. We can do just a certain number of iterations. But mathematically, we can define this in terms of infinities. Okay, and one example here, bottom right, this is actually an antenna, fractal antenna, which was used in one of the early mobile phones. So it says here 1999, and the reason, well, turns out that this it's like a chip. Well, it's an antenna that will be kind of encased in your mobile phone, and today antennas don't look like this, but this was one of the early iterations, and it had some very kind of efficient properties. So this fractal structure had, a fractal shape had efficient properties for basically kind of what for antennas, and you can kind of course, one of the conditions of having an antenna in a mobile phone is that it needs to be compact, it needs to fit into your pocket. Nobody wants to have, you know, like the old-fashioned antennas sticking out. So this was one way of sort of minimizing these. Okay, yeah, some examples here on the left is actually my sketches, and these examples we'll look at today. So these are basically these Lindenmayer, so L systems, so Lindenmayer systems of basically branching systems. Okay, so we can have a single branch, which is just a line, and then we split it into however many other branches we want. So, for example, we split it in this case into 2 branches. On the bottom left, we have splitting into 3 kind of splits, and then every branch can gets split kind of additionally or more and more. And that's a little bit kind of how sort of tree canopies are formed. Of course, here we have a very regular splitting. So there's always sort of at the tip of one branch, we have 2 branches that are created. In nature, this is not really how it works. So the rules are a little bit different, but there is a type of splitting because the splitting point does not need to be the same for both branches, for example. So there's some variations, but this is sort of maybe the simplest example. And then we can change, of course, the angles of how this opening happens, the reduction factor. Also, every branch that is created is smaller than the previous branch. So the branches get kind of smaller and smaller, and at the very end you have kind of leaves. And if we randomize these parameters, we get something that looks more natural, or so, because again, trees are not they're not perfectly regular, or so there's some randomization there. And I will show you both. So I will show you how the canopy looks like when you have just sort of the same parameters always, and when we introduce a little bit of noise or a little bit of randomness in, starts immediately looking more like a real tree. Okay, and here on the bottom left, this is the same algorithm. It just doesn't look so. It's because here we drew only the tips, only the last iteration. Okay, so only the tips of these branches are drawn here on the bottom left. So in a way, most of the tree you don't see. It's like invisible. You just see basically the canopy. And again, because all the parameters are the same, so for example, this opening angle is the same, the canopy has a sort of regular way of folding into itself, and then you can get shapes that don't look like trees at all. But again, they're created by the same by the same algorithm. Okay. This you can also use for production of or creation of landscapes. Again, I think it was 2 lectures ago, I talked about fractal Brownian motion, which is an algorithm used to generate basically terrains, so landscapes. And you know, in the term itself, the term is fractal Brownian motion. Also, you have some kind of specifically patterns that you basically you're adding these fractal components to itself, and then you have large features, and then you get smaller features and smaller, and this is how you can kind of create basically realistically looking landscapes. This is an example of a river flow. Or so if you, this is actually called, in physics, it's called preferential flow. Or so you have some usually granular medium. For example, this on the top right, you would have granular medium like gravel or earth or sand, and then you have fluid passing through it. Okay, water. Also think of a river flowing through a landscape, and then what happens is that as the fluid is trying to go through this granular material, or it's pushing the sand particles or earth particles around, and it's basically carving its way through the landscape. And the liquid or the fluid is basically following so-called preferential flow, or so it's trying to find the path of least resistance. And as soon as it finds it, it will kind of, the fluid will tend to take that path. Or so if you look at, for example, water running down the terrain, it's the water will always try to take, or not try, it will always take the fastest way down, but it will carry material with it. Or so it's also changing the material as it's moving, or changing the landscape itself as it's moving. And this combination, so this is like a feedback loop. This basically creates these preferential flow patterns. And then there's a whole theory called constructal theory, which I'm not even sure how scientifically accurate it is, but it basically is kind of trying to describe these again river basin flows. Again, if you look at them in detail, they look again a little bit like trees. So or like fractals, they have self-similar features where you have a big river and then smaller streams, and then even smaller and even smaller, they kind of branch out. So again, fractals appearing in sort of configuration of rivers. And here on the bottom, you see again 2 examples. On the left is the leaf veins, so veins in a leaf in a plant, and on the right you have this is, I think, the street network in Sana'a, Yemen, which is one of the oldest cities in the world today. So kind of an example of vernacular urban structure, and they look similar, and they look similar because they're like, even though they work on, they're like very different scales. On the left we have a leaf created by Mother Nature. On the right we have basically an urban structure created over centuries by people, but somehow they look eerily similar. And the reason is because they are trying to solve the same problem on 2 different scales. Okay, so the problem that they're trying to solve is actually the same problem, and the problem is how to reach every point of the surface using a structure that has 1 dimension lower. Okay, so I have a surface, and I'm trying to somehow have reachability of every point, but I have to use a 1-dimensional structure, meaning a line, or so structure that is 1 dimension lower. And in order to do this most efficiently, or I could try out different configurations, regular, irregular ones, but turns out that the most efficient way to do this is to use some type of fractal structure, or like these leaf veins are fractal structure. That means if you zoom in, these leaf veins, they look the same, or they just look like kind of branching structures. A little bit similar like in the urban fabric, where you have primary roads, So big roads, highways, then they branch into smaller roads, then they branch into, tertiary roads, and then they branch into maybe cul-de-sac kind of roads that lead to individual houses and so on. Yeah, so there's a kind of hierarchy of roads, and here there's a hierarchy of kind of leaf weights. Okay, I don't have the example, just want to run through it. Don't really have example here, but something similar happens, for example, in a dimension higher, when you're, for example, trying to have reachability of every point in space, using, again, a lower dimensional structure, for example, surface. And example of that is human lungs, or in general lungs. So what are your lungs doing? Your lungs are basically taking air and trying to basically absorb oxygen from it and put it into kind of transfer it into blood, and the other way around with CO2. The CO2 from the blood gets extracted, goes back into the lungs, and then goes out. So you need to have an exchange surface. There's an exchange surface. There's a membrane in your lungs. There's a membrane that basically where this exchange of CO2 in or CO2 out and O2 in happens. And this surface is folded. Okay, it's kind of folded, and it has a sponge-like fractal structure. Okay, if you would zoom into if you do a section of your lung and zoom in, it would look more or less like this picture on the left. It's just kind of in 3D. So these are not, these are kind of tubes, or they're not flattened, but they are kind of spatial. Again, this is the way to compact the maximum surface into the smallest volume. And this is an optimization problem. Okay, and why is this necessary, or why is this happening? Well, because we want lungs, in order for them to be efficient, we want to have the largest exchange surface, or because we want to be the most efficient in exchanging this, O2 and CO2. But lungs cannot be infinitely big, or they cannot be very large. Like lungs are, it's an organ, it needs to be compacted. It needs to be, in a way, very efficiently compacted into our bodies. So Mother Nature basically found this way of compacting this very large surface into a small volume, and that's basically our lungs. And many other tissues in our body, and in generally in animal bodies, work exactly the same way, like in kidneys, exchange or filtering of blood in kidneys. I guess probably also liver, same way. So these fractal tissue structures appear also in our own bodies, not only in kind of plants. Okay, they're in a way all over. If you look closely, you will see that they are just everywhere in nature and in civilization. Okay. Yeah, some more examples of these fractals. This is actually, again, this is now specifically this Lindenmayer system, and this is directly from his book. So basically, he is defining these. Basically, he's defining a shape grammar. Okay, so Lindenmayer systems are described through shape grammars, and here you have basically written out formulas that enable you to basically generate these shapes. When I say formalize, I mean, there's some kind of F, or so usually you would start with a primitive. There's some primitive shape, and then there's a production rule, which is just a function that takes the shape and produces something else. And then the idea is that you would kind of apply this recursively as many times as you want, or as many branches as you want to have. And yeah, in order to get even more realistically looking plants, you cannot have this branching at the same point. You need to have a little bit more. You have to add just a few more parameters, and here they are described kind of how this branching is exactly happening. And if you implement just this rule here, then you can basically get any tree in the world. Yeah, and variety is kind of very, very large. Okay, axial tree, and this is actually called the Horton-Strahler analysis of branching patterns. Okay, so that already went, but this was already, the book was written 30 years ago, so these are not really new topics. They are kind of already well researched. Okay, And Steiny is a professor at MIT who wrote, or he was the guy who first defined shape grammars. So he was basically just looking at formal grammars defined originally by Noam Chomsky. It was 60s or 70s, and at the time when formal linguistics was just starting off. Then you had formal grammars, and then Steiny was basically a designer, and he just decided to, or was kind of using this computational system to describe how certain designs are made, or to call it just shape grammars. But these are basically just formal grammars. And he, for example, described the rules of designing a Victorian villa, or also Palladian villas. Or so Palladio was using basically, he was using very formal rules to create his designs. And even though he couldn't, of course, express them in terms of algorithms, he used, these rules you can for sure express like that. Okay, this is an example of, I think it's one of the kind of a window tiling patterns or something like that. Okay, and here's actually, George Steiny and William Mitchell, the Palladian grammar, are so basically a description of how Palladio, in a way, generated his villas through using the language of shape grammars. And here is the Frank Lloyd Wright's prairie type houses, kind of also describes in the language of shape grammars. Again, there's a lot more literature on this and on this topic, and it's also being researched actively today. So there's a conference called ARK-E, which happens every year. At least before COVID it happened. I think it still happens, maybe in a virtual form. And every year there's like, there would be a session where there'll be multiple presentations just on the topic of shape grammar. So it's still an actively researched field. And today we will be looking at this example of subdivision. Again, subdivision is another it's another fractal pattern. Or so here we could take a polygon and we can start subdividing it, or through using a centroid. Or so we define a centroid, which is like a central point, and then we subdivide it into triangles, and we continue subdividing these triangles as much as we want, or as far as we want. We can use the same principle again to generate landscapes. Or so if we subdivide but then also do shift, and then we do this over and over, we are in a way applying this fractal Brownian motion, or just in a bit of a different form, but the effect is the same, and we can get kind of a naturally looking sort of fractal landscape. And this on the bottom, that's exactly the example that I'll show you today. So this runs in Rhino. We take a primitive, meaning a shape. We can have a box, or dodecahedron is the other option. And again, you do subdivision. So you divide, for example, a face, and you say now this face will become a pyramid, okay, or a truncated pyramid. Or it means it's a pyramid that is kind of cut off, and then you get a shape here, and then you just continue. Okay, you continue with that. You continue applying rules. One additional parameter that you can do is you can remove when you do a truncated pyramid, you can remove this top, or so you can say the top now doesn't exist anymore, and so there's a kind of a hole. And if you apply this few times, you can get very kind of intricately looking shapes. I think we can have a look. I think this was 6 or 7 iterations, this model here on the right. And this is in the end kind of OBG, so you can then you have it in Rhino, and then you can do many other operations on them. And I'll show you some other examples. What happens when you take this principle, just push it to the extreme. And that's actually it for the lecture. There are two very good readings that I would recommend. So already before mentioned, The Algorithmic Beauty of Plants by Aristide Lindenmayer from 1990. It's quite a thick book, but actually I found a PDF online. I think it's free, or at least I found it free online. and I made it available to you. So if you go on our into our text folder, you will actually find the whole book in PDF, so you can run through it. There's some hundreds of pages, but I think it's yeah, it's very, very good textbook on this topic, and it's basically a standard. And then a bit more recent meshed grammars from Michael Hannesmeyer and Benjamin Dillenberger. Benjamin Dillenberger is now a professor at ETH Zurich. He's leading called Digital Building Technologies Group, DBT, yeah, Digital Building Technologies Group. And you know, in these 2013 and around these years, he was basically using exactly this algorithm here, subdivision algorithm, to basically create designs, and then he was also 3D printing them. And these mesh grammars basically just extends the story of shape grammar, so just apply the meshes. Or so the idea is that you have that you would define very ornate structures by just using this language of recursion, of shape grammars, of yeah, and then kind of, I think in the last years, most of the research of the group went in the direction of kind of using these shapes to for creating kind of optimized structures, which are then 3D printed or somehow fabricated, brought into the real world, and actually used for construction purposes. Or even though at the very beginning, in this kind of early 2010s, these were just computational models. You can have a look at this project called Digital Grotesque. I think I used it as a reference, at least in one of the other lectures. That just kind of shows those principles basically just blown up in the real world.